In this video, we will be looking at energy balance for both closed system and an open system. So now let's start with the closed system. So closed system. So now when we say a closed system, what is a closed system? A closed system refers to any system that allows the exchange of energy. So when you have our system in this format, so this is a closed system, right? It allows the exchange of energy, but it does not allow the exchange of matter. Now, you can see energy enters, energy leaves, energy enters. So it allows the exchange of energy, but it doesn't allow the exchange of matter. So the matter here I'm referring to is material. So let's see any substance. So we can just assume it to be a closed system, something which has been closed. So we can't put anything inside, but then we can add heat to it. It can also lose heat to the surroundings. So that's what we refer to as a closed system. Now, for an open system, I would like to treat them separately. So now, this is our closed system. Now, to look at the energy balance for a closed system, we have our closed system, and we have to do our energy balance. So the energy balance means that what you are trying to say that energy can neither be created nor destroyed. So our energy in should be equal to our energy out. Yes. So energy in is equal to energy out means that the energy that we put into the system wouldn't be exhausted, but then to be converted to other forms of energy. And that's where our first law of thermodynamics comes in. Our first law of thermodynamics says that energy can neither be created nor destroyed. Right? So in a mathematical form, we have Q minus Ws equals change in internal energy plus change in kinetic energy plus change in potential energy. So our Q here refers to heat. Now we said that the energy closed system allows the exchange of energy. So now the energy here is in the form of heat or work. Right? So we call it a function of heat and then work. So anytime you see heat and work, that's what we call as energy. Of course, you don't have the same unit as joules. Right? So now this is our first law of thermodynamics in a mathematical form. Our Q here is Q is heat. WS is work. But then to be more specific, because you'll be treating both closed system and open system, we call it shaft work. Right? Shaft work. And so our shaft work refers to any work which is being done by the moving parts. Right? So anytime you see a piston, that's for closed system. Mostly we use piston. So you see a piston, that means the work being done by a piston is called a shaft work. And then our change in U here is our internal energy. Now, internal energy refers to all other forms of energy aside kinetic and then potential. So, for we chemical engineers, we call it chemical energy or internal energy, still the same thing. And then our K here refers to our potential kinetic energy. I guess you all know what kinetic energy is. And then our PE here is called potential energy. So the energy associated with the moving parts of a system is called a shaft work, right? And then the kinetic energy is the energy due to the motion. So it refers to the motion of the molecules, right? And then the potential energy is, we know potential energy due to the position, or if there's a change in position. Once you are considering changing potential energy here, then changing kinetic energy, right? So changing kinetic energy is much related to the change in the movement of the molecules of the system. Now, when you see a system refers to anything we are discussing. Right? So when you have a problem, we see that a gas in a cylinder. I mean, the gas here is now our system we are dealing with because that's what we are talking about here, not the cylinder itself, basically. And then our shaft work is due to the moving parts of the machine or due to the moving parts. Yes. So kinetic energy here, sometimes some students get confused. Kinetic energy here is actually related to the moving of the molecules or the movement of velocities associated with the molecules of the system. But our shaft work is with the moving parts of the system. Now when we take our system, let's see our cylinder, and we have a piston. So the energy associated with the moving part, which is the piston, because the piston goes up and down. That work associated with that is called the shaft work. But then the molecules of the gas moving at one state to another state in the form of velocity is what we call the kinetic energy. So this is what we'll be using in our calculations for CPC2, that is for closed system. Now let's define the terms further. Now, when we say heat, we know that for closed system, heat is being exchanged. Of course, heat is energy, right? So when heat is being added to the system, when you have heat added to the system, it's positive, right? And then you have heat lost from the system, that is negative. So when you have a person who says that 80 kilojoules of heat was added to the system, that means our 80 kilojoules is actually positive. When we say 80 kilojoules of heat was lost from the system to the surroundings, then it becomes negative. I hope you understand that. Now let's move on to the shaft work thing. So with the shaft work thing, we understand what the shaft work is now. Now in the shaft work thing, because we are using this convention, Q minus W, there are two forms of the thermodynamics. The law of the first law of thermodynamics. So you have the Q minus W equals our energies, right? And we have Q plus W. So now with the Q plus W, for both systems, for both situations, the Q's have the same definition. So heat added to the system is positive, heat loss is negative. But now, for K plus WS and the K minus WS, the work, the shaft work, they have different or let's say opposite definitions. So now for this, we are dealing with K minus W. So WS is positive. So it's positive when work is done by the system. So when work is done by the system. And then WS is negative when work is done on the system. So let's take note of these two. So we shouldn't be confused. When you have a question which says that 200 kilojoules of work was done by a piston. So now, since the work is being done by the piston, it's done by the system, by the piston on the system, right? So it follows this. So it follows this. Work is done on the system because you are seeing that 200 kilojoules of work done by a piston. So now the work becomes negative 200. When we want to substitute that into the first law of thermodynamics, it becomes K minus negative 200. And that gives us K plus 200. Now, when we see that 200 kilojoules of work was done by the system, then it becomes positive. Now, our first law of thermodynamics becomes K minus 200 because our 200 is positive. You just have to substitute it there. So now, so that's all for the first law of thermodynamics for a closed system. You just have to know the conversions very well. You know work is positive when work is done by the system. Work is negative when work is done on the system. And then for the heat, they are the same. Heat added to the system is positive. Heat lost from the system is negative. We'll be looking at this, not the Q plus W. Right? Now we can just move straight to open systems, and then we can go ahead and solve few questions. So now when we say open system refers to any system that allows the exchange of both mass or material and then energy. With open system, it allows both material and then energy to be exchanged. But then the closed system allows only energy to be exchanged. There's no exchange of material. I guess you know the difference between the two. So now when you say open system, so let's say our system here, it's open, right? To a lame person, it's open like this, and then we can add materials to it, probably maybe 200 tons of kerosene. We can just pour, and then it's leaving, right? It's open, so it enters and it leaves. And then energy also is being exchanged. Of course, energy is in the form of work and then heat, similar to the closed system. Right? But then there's a slight difference, and then I want us to look at that. Yes. So now for a closed system, we know that our Q here. So our first of thermodynamics actually doesn't change. Q minus WS. So this for our closed system is equal to change in U plus change in K plus change in potential energy. Right. Now, for the energy balance from first law of thermodynamics, it doesn't have anything like with respect to closed system or with respect to open system. But then it has a general formula which is Ko minus W is equal to change in U plus change in kinetic energy plus change in potential energy. Right. So this is the general form. So now the work here is shaft work plus flow work, right? But then for closed system, there is no flow work. Why? Because there is no exchange of material. The flow work is associated with the exchange of material. So it's the work that's actually as a result of material input and then material leaving the system. The material, whilst you are putting the material inside and then the material is leaving, that's work on the system. Or yes, so let me see it that way. And that's what you call the flow work. But then because closed system has no material input or material output, there is no flow work. And now its term becomes just Q minus WS because change in U blah blah. So that's what you have here. But now we are dealing with open systems, right? Let me write it here. And then for open systems, there is both flow work and then shaft work. Now when you consider the general expression for first law of thermodynamics, the work here now becomes shaft work plus flow work, right? For open system. Now what we do is that we just write Ko minus everything here, Ws plus Wf, going into change in internal energy plus change in kinetic energy plus change in potential energy. Now our Q minus Ws minus Wf is equal to change in U plus all these, right? So let me just use a spreadsheet, right? So we can transpose Wf to the other side and see that Ko minus Ws is equal to change in U plus Wf plus this. So now let's define our terms. Our flow work here is actually PV. So now when you want our change in flow work, because the flow work is as a result of material input and material output, when you want the actual magnitude of the flow work, our flow work now becomes PFVF minus PIVI. So now our F here refers to final, right? So the one leaving. Then our PIVI here is the one entering. Our work, shaft work here can't really be solved for because it's actually a work associated with the moving parts of the system. So like it's like they give it to you in the question, or you can solve it from the equation. But then actually putting a fixed equation for it is not possible. So Q minus Ws is equal to change in U plus. Now flow work becomes PF VF minus PIVI. So let's neglect our kinetic and potential energy terms. Right. So I want us to yes. So Q minus Ws is equal to change in U plus PFVF minus PIVI. So we have our other terms there, but we are neglecting the kinetic and then the potential. Now this is change in U. So change U is also equal to U final minus U initial. So Q minus Ws becomes U final minus U initial plus PFVF minus PIVI. So now we know that enthalpy is equal to U plus PV, right? So that means our UF plus our PFVF here will give us HF will be equal to UF plus PFVF. And then our UIPIVI also give us HI is equal to UI plus PIVI. Now let's write it well. UF plus PFVF Now this is minus, so we can bring a negative here and then open bracket ui plus pi vi. So now our uf plus pfvf is actually hf, right? So Q minus ws is equal to hf minus ui pi vi also give us hi. So hi, and then you can add our terms kinetic energy plus potential energy. Now hf minus hi gives us change in enthalpy. So Q minus ws is equal to change in enthalpy plus kinetic energy plus potential energy. So now for an open system, this becomes the first law of thermodynamics for an open system. The terms are the same as closed system. Our Q is positive when heat is added to the system. Our Ws is positive when work is done on the system. When work is done by the system. So the same conversions apply to the same. But the only difference here is that when you look at the closed system equation, it's changing internal energy, but then the open system is changing enthalpy. So that's the only difference between the two. Otherwise, everything is still the same. So sometimes you can have a question that says that your kinetic energy can be zero and your potential energy can be zero, and then you just be having Q minus Ws is equal to change in enthalpy. So this is for an open system. Please don't write this as a closed system anywhere. And then Q minus Ws is equal to change in internal energy. It's now a closed system. So this is for a closed system. Yes, so that will be all. Our next video will just be solving questions under open system and closed system. And then one thing is that to identify open systems, we have some things to look out for. So now with the closed system, I said that the shaft work is actually related to piston. But for an open system, its shaft work is actually related to turbines, compressors. Right? So anytime you see a turbine or a compressor, just know that what you are dealing with is an open system. And then you see flow rate. So probably you see kilogram per hour, mole per hour. That means it's entering and then it's leaving. Right? So it's an open system. Right? So let me just do a short table to distinguish closed system and open system. So that was set as a guide. Right? So closed system, open. So open, we see flow rate, whether mass or moles. It's in flow rate, which is kilogram per hour or kilomole per hour. But for closed system, they see masses or moles. So something like kilogram or kilomole. There's nothing like per hour. And then for closed system, we see systems like piston, closed cylinder. Right? But for open system, we see something like compressors, turbines, pump, yes, and conduits, yes. So that will be all for now.